In today's lesson, we're going to go ahead and take notes on characteristics of exponential functions. We're going to first look at tables. We're going to look at a linear function table first. We know it represents one when we have a constant rate of change between the x values and a constant rate of change between the y values. What that looks like is going ahead and seeing the first x value of -2 and figuring out how I get to the next x value of -1. That will be a change of +1 to get there. Then again, I keep going. X value is -1. The next one is 0. How I get there is by adding 1. After 0, the next x value in my table is 1. How I get there is by adding 1. And then last but not least, to get from 1 to my next x value of 2, I also add 1. As you see, it was +1 every single time. Let's look at the y values. Same idea. Take the first y value, -8. How do I get to a -5 from -8? I must add 3 as my change. To get from -5 to -2, I must again add 3 as my change. To get from -2 to 1, I must add 3. And then to get from 1 to 4, I must add 3 as well. As you see, a constant rate and number. When we answer the characteristics below, we want to pull the y-intercept from our table as the value when my x is 0, and then my y is a number here. So again, your y-intercept is always going to happen when your x value is 0. The change in y is what we had in purple above. That was +3. The change in x between all x's was a +1 that we had in green up top. And then we go ahead and find the slope in our table. The slope in our table is always going to be that change in the y value, which was going to be 3 across the board, all over the change in our x value, which was going to go ahead and be 1 here. It's always got to be the y over the x. Make sure you remember that for slope. Then we go ahead and actually divide that down. 3 divided by 1 will come out to be 3. Let's look at an exponential table. We know it's going to be an exponential table when we have a constant rate of change between the x values, but the biggest thing is that we're going to have a common ratio between the y values found by the following. I'm going to let you know that ratio is going to indicate we're going to be dividing here. So I'm going to go ahead and divide specifically the change in y divided by the previous change in y. We go ahead and pull the characteristics from the table above. We want to list the y-intercept here, and as a reminder, that's going to happen when your x value is 0 in your table. So that's the first row. I'll just copy and paste as a point. For the change in the x values, we want to go ahead and see how you get from the first x value of 0 to the next x value of 1, and that will be a change of 1. How do I get from 1 to 2 is also add 1, change of 1. How I get from 2 to 3 is by adding 1. And then again, how I get from the 3 to the 4 last x value in my table is by adding 1. So as you see, we have the same constant change for our x values, so that meets the first criteria. The second criteria is we have to have a common ratio here. So that means I'm going to look at my change in my y values. Between the first and second y value, I went from -1 to 1, so that will be a change of +2. I go ahead and see how I get from 1 to my next y value of 7. That will be adding 6 here. So notice right away it's not linear because I just wrote 2 different numbers. We go ahead and see how we get from 7 to 25, our next y values here. That's again going to be +18. How I get from 25 to 79 is by adding 54. So I'm going to write down all those change in y value numbers. That would be my 2, then my 6, then my 18, then my 54. I just wrote above. How I find the common ratio is again by dividing the change in y by the previous change in y. So I'm going to go ahead and take the first 2 changes of 2 and 6 here to show you how we do that. I take the change in y and divide it by the 1 prior. That's why I'm doing 6 divided by 2 instead of the other way around. That comes out to be a 3 here when we actually do that division. Let's go ahead and check the next one. So same pattern is going to happen. I'm going to take the change in my y value and divide it by the previous change in y, which will be 6. Again, that's why I do 18 over 6. When I divide 18 by 6, that gets me 3. Last one to check is my change in y of 54 divided by the change prior, which was my 18. Again, when I do 54 divided by 18, that comes out to be 3. That's what I was talking about common ratio here. They all have the same common ratio of 3, hence why it will be exponential, and why the common ratio of the table will be the 3 we just found by dividing the change in y by the previous change in y. Example 1, which is determine if the table is linear or exponential, and then answer the questions that follow. We go ahead and look at the change in our x values for the first table. To get from -6 to -4, I will add 2. To get from -4 to -2, I will add 2. And as I see throughout my table, my pattern will continue. So I definitely have a constant x. Let's look at my change in y. To get from 37 to 27, I subtract 10. To get from 27 to 17, I subtract 10. To get from 17 to 7, I subtract 10. And to get from 7 to a -3, I subtract 10 as well. So right away, I wrote the same number for the change in my y values. So I'm going to go ahead and make sure I know this is a linear function here. I pull the y-intercept by just writing the row that has my x value being 0. So that point is 0, 7. Slope, if linear, well, it was linear, so let's go ahead and do the slope. Remember, that's the change in y over the change in x. So I'm going to write the -10 that I found was the change between every single y value. And I'm going to divide it by the +2, which was the change among all my x values here. When I do -10 divided by 2, I get a -5 for my simplified slope of my table. Let's look at the change in x values for our next table. To get from -4 to -3, I add 1. To get from -3 to -2, I add 1. And to get from -2 to -1, I add 1 as well. And throughout, it is a constant rate of change. Let's look at our y values. To get from 3 to 6, I will be adding 3. To get from 6 to 12, I will be adding 6. So right away, not the same number. We add 12 to get from 12 to 24. And we add 24 to get from 24 to the next y value of 48. So right away, I'm going to go ahead and state that this one is exponential here. The really big reason why is because remember, now we can actually figure out these changes here. So I do the change in my y value divided by the previous one. So that's why I'm doing 6 divided by 3 to get 2. Change in y divided by the previous change in y, that's 6 divided by, or from 12 specifically, which is going to go ahead and be the 2 here. And then we go ahead and check our last one as well. 24 divided by the previous change in y value, 12, comes about to be the 2 here. So as you see, all the change in y over the previous change in y comes out to be the common ratio of 2. It's the same across the board, so that's how I know it's exponential. From here, I go ahead and highlight my row that has an x value of 0, y value of 48. That will be my y-intercept. Because this was not linear, I do not have to do the slope. We go ahead and look at a context problem. The table below shows the data collected from growing bacteria in a petri dish. We want to look at the number of hours, see that change between the x values here. From 1 to 2, I have a change of 1. From 2 to 3, I also have a change of +1. And from 3 to 4, I also have a change of plus 1. Constant, let's look at the y values here. To get from 320 to 400, remember that this y value is representing the number of bacteria. I go ahead and add 80. To get from my 400 to the next y value of 520, I go ahead and add 120. And then I go ahead and take a look at my 520, how I get to the next y value of 760, and that will be adding 140. From here, to truly check that it's exponential, even though I have a really good hint because those y values have different changes between them, I'm going to go ahead and divide the change in my y by the previous change in y. When I do 120 divided by 80, I get 1.5. Let's check the value for the 140 between the prior change in y, the 120 in front of it. This comes out to be 1.16 repeating here, which I know is not the same value as the common ratio between the first two values, but because this is a context problem, it's a real-world situation and not perfect. We're going to do our Desmos application number 1, which is going to be selecting all the tables that represent an exponential function. The cool thing is we could put these tables in Desmos by hitting the plus table button, and then we'll type it in the X and the Y carefully. We'll look at the shape of the graph with the zoom fit button, which is this little magnifying glass with a plus inside, to see what shape it looks like. Think back to last class where linear made a nice straight line and exponential made a nice curve, kind of J-shaped. Let's go ahead and see. I go ahead and put plus table, type it in, and you want to hit the zoom fit button. You should be pausing if you need to get that table in and follow those steps. But once you catch up to me here, go ahead and see that it is not a straight line. This is looking like that exponential growth curve here. So we're going ahead and selecting this table. And I go ahead to my next table. Again, take a second to pause, plus table to put it in. Hit the little zoom fit magnifying glass. And as you see, those points are nicely spaced out with a constant slope, making a straight line. So that's linear. We go ahead and check the next table. Zoom fit it. That is definitely curving, making that exponential J-shaped graph that we did last class. So we're going to go ahead and select this one here. I'll cross off that second table, by the way, because that one was linear. And then let's check the last one since it is a select all. We go ahead and hit the zoom fit after hitting plus, then putting the table in. Again, you should be pausing and making sure you're doing this along with me. That's going to give us a linear line, evenly spaced out points, no curve to the graph, so it's linear, not exponential. Let's look at those shapes now on our graphs. This is going to be our linear shape like we just saw in Desmos. And again, as you see, these points are curving up, not perfect spaced slope away. That's going to be our exponential function. Let's take our note here that you may see all the following domain notations to represent all real numbers. The first one's like we've done before, where we do negative infinity being less than x, which is less than positive infinity here. In parentheses, soft brackets here, you'll see a negative infinity, comma, positive infinity as well. Just another way to notate all real numbers. Last one is that fancy R rewrite that we saw at the beginning of the year as well, our symbol for all real numbers. Let's talk about our characteristics of graphs of linear functions. As a reminder, they're always a straight line, just like we saw in our last Desmos application. And the slope between one point to the next is always going to be the same for the entire graph. Speaking of slope, let's find it for this graph here. We go ahead and count the rise, which is going to be up 1, always over the run here 2. We're going to go ahead and count over 2 spaces here. That will be our run, which goes in the denominator of our slope fraction. When I do 1 divided by 2, it comes out to a decimal, so I do want to go ahead and leave it as the fraction of positive 1/2. That's our slope of this line. The x-intercept is going to be where the line crosses the x-axis. Let's write it as a point, -2, y value is 0. Remember from our table, the y-intercept has an x value of 0. Specifically on a graph, it's going to go ahead and be where your line passes through the y-axis, which is at a +1. The domain, look at the left side of the graph. You have an arrow going to all the way left, so that's going to be a -infinity. Less than x being less than on the right side an arrow to +infinity. As a reminder, when we have negative infinity and positive infinity, that's going to be our all real numbers. We can write that notation. Don't forget, you can also see it as negative infinity, comma, infinity inside parentheses here. The range is going to be the same exact thing because at the bottom of the graph, I have a negative infinity. But be careful because the range is the y values from bottom to top. So we'll put a less than y being less than the top arrow of and going to positive infinity. Again, when we have negative infinity to and positive infinity, we have a all real number case. And you also might see it in the notation of parentheses, negative infinity, comma, infinity, closing those parentheses down. F of 1, remember when it's inside the parentheses, it's going to go ahead and be our x value on the graph. So I find where my x value is 4, and I'm going to count up how far for my y value of my point, which will go ahead and be 3 here. Let's do the next one. Same idea. We're finding -2 on the x-axis. This time I don't have to go up or down. It's right here with a y value of 0. Be careful for the last one because now you have the y value of -1. Looking on our graph, the only time we have a y value of -1 is when it's all the way left at the x value of -4. Just got to work backwards there. You had the y and needed the x value that y value is located at. Let's go ahead and talk about graph of exponential functions. They're a little bit different. Their shape is more of a J-shaped graph, and they'll have different quote-unquote slopes between points. We don't really have slope of exponential functions. That's why I put it in quotations. But I think it helps to relate the two. But as you see, if I count rise over run between this point to this point and this to this, it is much different of a slope. So not a constant slope there. We never cross the horizontal asymptote here. And as a reminder, last class we learned about the horizontal asymptote. It's a do not cross line, and it's going to be just below our graph here. Let's go ahead and fill in the following characteristics using the graph of function g above. We go ahead and have the horizontal asymptote, like I just said, being at -3. I want you to go ahead and underline that it's a horizontal asymptote because that's going to give me the equation of y equals. When we draw a horizontal line like we have done before, we always make sure it's a y equals 1 passing through the y-axis at that specific value. In this case, it's going to be -3 because my graph stops and never goes below that value or doesn't even reach that value either. It will get so close but never touch it. The y-intercept is where our exponential function crosses the y-axis. It's going to be having an x value of 0 and a y value of the -1 here. For domain, let's look at the left. On the left side, I have an arrow going to -infinity. And on the right side, I also have an arrow that will stretch to positive infinity. That's going to go ahead and be negative infinity being less than x being less than infinity. You can also put it in parentheses, soft brackets with negative infinity, comma infinity. Or you can write the fancy R. We want to make sure we know all three notations at the top of our page. Range is different though, be careful, because I have a do not pass line at -3. So I need to include that do not pass 9 in my range here. For -3, I go ahead and remind myself that would be y here because range is the y. And I have to stay above that -3 value. So when I say above that -3 value, that's going to go ahead and be a greater sign for that -3. Another way we can write this is has -3 as our lowest value possible, but not including that because, again, I can't touch that horizontal asymptote. I have to stay above it. And I would keep going to infinity. Either way you write this notation is fine. But again, how I get it is knowing that my graph has to be above -3. So I use the greater than, or I can have -3 as the lowest part and infinity as the highest part of my graph, bottom to top. We go ahead and do g of 1 here. So again, that's going to be the x value I'm looking for here on my graph. When my x value is 1, I go up to the y value, which would be 3 here. When I have g of 0, that's my x value being 0 now. I go ahead and look at when my x value is 0. Going down to my graph, the y value would be -1. Make sure we go backwards for the last one here. We have the y value given as 3. When I go up to my y value of 3, I'm going to go ahead over on my graph to the x value that it would match with, which is going to go ahead and be this x value of 1. We're going to try example number 2, filling in the characteristics of the graphs below. We'll start with the y-intercept, which is going to be when the exponential graph passes through the y-axis. That's going to be at the point 0, 1.5. You can also put 1.5 as well. We're going to go ahead and talk about the asymptote here, which is the line of do not pass for our exponential function. Our exponential function is going to get so close but never pass this y value of 1. And as a reminder, since it's a horizontal line, that's why we put y equals the value of 1. For the domain, we're looking on the left side of our graph, which is an arrow to -infinity. And then we look at the right side of our graph and also see an arrow that will keep going to positive infinity. So that is our all real number case. As a reminder, you can notate it in any of these 3 ways, and you might see them all. For the range, I'm always going to start by setting up y because range is my y value. I will pull down the asymptote because that's the do not cross line. And all I have to decide is what's going to go ahead and be between my y and my 1. A less than sign or a greater than sign is my only 2 options. Now, we remember that range is bottom to top. So your lowest value is 1 at the bottom of your graph. You cannot pass it. And the highest value has that top arrow going up to infinity. So that's why I'm going to say this is greater than 1 here. Again, how you can notate it as well is to be from 1 to infinity here. F of 2, as a reminder, you're looking on your graph where your x value is 2. And you want to answer with the y value, which would be 3. Working backwards now, you want the x value to be found, and you're given the y value of 2. When your y value is 2, your x value is 1 here. Let's look at our next graph. We have our y-intercept again being the point where the exponential graph crosses the y-axis, specifically here at the x value of 0 and the y value of -3. The asymptote, remember, is y equals since it is horizontal. The line of do not pass is going to have my graph getting so close but never passing the 0 here. It's just where my graph cuts to the left. We go ahead and talk about the domain. Again, being everything going left with that arrow to -infinity, and everything on the right side with that arrow going to positive infinity. That's our case of all real numbers. Remember, we can notate it any of these 3 ways. For range, let's set it up. Remember, I said it was y. It was taking your horizontal asymptote number, and now you just got to decide, is it a less than sign or a greater than sign? Well, look here this time. 0 is the absolute top of my graph, so it has to be everything below or less than in this case. How we notate that in another way is negative infinity to 0, again because it's got to be our range bottom to top, lowest value to highest when you're writing that interval notation. True or false? F of 1 is a negative 9. Well, when my x value is 1, my y value is indeed negative 9. Talking about this point right here that I bolted, so that's true. When my x value is negative 1, my y value is also negative 1 as well. That's again a true statement where your x and your y match up here. Writing that point in function notation. Let's look at our Desmos application number 2. Given the equation f of x equals 1/3 times 3 to the power of x minus 5, we want to select all that are true. The first step is you're going to put in the given equations, the one I just read, and then we're going to go ahead and put each h parenthesis with a number inside separately to see if it does come out to equal. So I put in the given function in line 1, and then I'm trying each of the 4 options here. As you see, I just put the letter of the function and the number in parentheses, and I let the gray boxes tell me if they're going to match up with the ones on my paper. I go ahead and see that the only two that are true are going to be the first and the last one here. H of 1 does come out to be negative 4. As you see, h of 6 is actually 238, not negative 3 here. H of 4 is actually 22, not 3. So these are the only two we can select here. I'll go ahead and shade them, and you should as well. We want to recall from the notes of last class, how can we tell that we have a linear equation versus an exponential equation here? Our linear equation will go ahead and be very much sometimes in the form or easily able to be put in the form y equals mx plus b. We'll have the m be 4 and the b be 1 for this case, just to put an example down. And the biggest thing is that the variable x is going to be multiplied here. When we have an exponential equation, let's write one similar. Y equals 4 to the power of x plus 1. As you see, the x variable is no longer multiplied. We have the variable as an exponent here. So again, for our linear, that's going to be the first example here. Let's label it. It's going to have the variable multiplied here. For our exponential, our second example here, that's going to have the variable, our letter x, in the exponent position. Now that we have equations of linear and exponential functions, we actually want to apply them here. We can easily always find a y-intercept or f of 0 of an original function when we replace the x value with 0 here. So go ahead and keep the negative 1/4, but instead of x, I'll replace it with 0, and I will subtract 8 here. F of 0, again, make sure you do your order of operations, which tells you to multiply negative 1/4 times 0 first, which is 0. And then you subtract by 8 to get f of 0 equals negative 8. That gave you the y-intercept. We'll go ahead and just write it as a point here, which is going to be an x value of 0 and a y value of negative 8. The same thing's going to go ahead and happen for our exponential here. I'll go ahead and replace my x value everywhere I have it in my equation with 0. This time, because we have an exponent, we want to think about our exponent being done first. Since it's PEMGAS, GEMGAS, the order of operations requires the exponent to come first. 3 to the 0 power, think of that 0 power rule where anything to the 0 power just becomes 1. That 1 will then get multiplied by the -2 and added by 7. Order of operations tells us to do multiplication next in PEMDAS and GIMDAS. So that's -2 times 1 and -2 before I finally add 7 as my last step. That's going to come out to be a positive 5 in this case here. When I rewrite it as a point, since it is a y-intercept, I do want to do so. I go ahead and have the x value being 0 and the y value being 5. So no matter which equation you have, you can always go ahead and replace the x with 0 to find your y-intercept when it's equation format. We go ahead and go back to our linear function, and as you see, we want to find f of 4 here. That means this time, instead of replacing 0 into my x, I'm replacing 4 into my x value here. As a reminder, I like to multiply a fraction by a fraction, so that's why I put 4 over 1. That helps me get a -1 times 4 up top, which is -4, a 4 times 1 in the denominator, which is a positive 4 here. Then I'm able to divide -4 by 4 to get a -1 that I will then subtract by -8. -1 minus 8 is going to go ahead and be -9. And the notation you'll see a lot for it is called f of 4 equals -9. Something different for exponential than linear is that exponential will always have the horizontal asymptote. The horizontal asymptote is the line of do not pass. How you pull it from an equation instead of a graph is it's always going to be the value that's added or subtracted here. So I'll pull down the 7 because that's what's added or subtracted in my exponential function. And remember, because it's horizontal, we have to put it as y equals that added or subtracted value here. We're going to pull the domain and range from our equation now. As a reminder, domain is the x values, and it's based on what kind of equation we have. Since this f of x equals -1/4 x minus 8 is a linear function, we know and go ahead and state what our linear domain is. When it's a linear function, it will always be all real numbers, so -infinity to +infinity, as well as -infinity is less than x, which is less than infinity here. You can also notate it with the all real numbers symbol. Again, the range is based on what type of equation it is. Because it's a linear equation, again, we know our lines, linear functions have all real numbers for our range, -infinity being less than y, which is less than infinity. Writing it in any of these three notations will work out here. We go ahead and look at the domain of our exponential equation. Because it's an exponential equation, we go ahead and know the domain's going to go ahead and be all real numbers as well. So that's going to be -infinity being less than x being less than infinity, -infinity comma infinity, and then writing the all real number case. The range for exponentials is not always real numbers, because as we talked about in the last page, we had that do not cross line. Let's pull down the number, which was 7 for this case here. Because we had 7 and the range is y, remember we set it up with y, and what we fill in between them is either a less than or a greater than. You got a 50-50 shot, but let's actually get it correct by looking at our equation we are given. It is g of x equaling a -2 times 3 to the power of x plus 7. And that negative right away here is going to go ahead and tell me that I have a flipping over my x-axis here, which means my graph's actually going to go down below my 7 here. So that's why it's going to go ahead and be y being less than 7. As a reminder, we can also write it as -infinity comma 7 in our parentheses here. The biggest thing is that you will have Desmos to be able to graphic, get a visual here, and I'll show you that we can check the range accordingly there. Checking my given equation in Desmos here, I type it exactly in as is, and as we can see, we have our graph going so close but never reaching 7. And it's going to be everything less than that. That is where my red line graph is happening here. In general, we go ahead and remind ourselves that linear equations, domain, and range is almost always all real numbers. Again, in general, exponential equations domain is almost always all real numbers. Exponential equations range is almost always going to be y being greater than the horizontal asymptote value we have. And as a reminder, that will be equivalent to the horizontal asymptote, comma, infinity in our parentheses interval notation. Or we're going to have y being less than the horizontal asymptote, just like we saw because our graph was flipped down because of that negative. Look for that negative to know. We are going to go ahead and have negative infinity to the horizontal asymptote in our parentheses for interval notation. And again, the biggest thing I just mentioned is that we'll have the negative in our example to help us know when that is the case for less than. So know that these each are equivalent of each other. We're going to have an exception though. We are going to have times where the domain is restricted in the directions given to you, as well as we're going to have to restrict the domain in certain contexts because there's some things that just don't happen in the real world. Let's go ahead and read our context example number 1. Wonderville has a population of 1,000 people. Every year the population will increase by 5%. The function can be represented as y equals 1,000, parentheses 1.05 raised to the x power, representing the growth where x is the time in years. So we want to go ahead and notate that the x is going to be our time in years here. Because that's our domain, we got to think about what we know about years to restrict our domain for our x values. Well, I know I cannot have negative years, as well as I know I can start at the year of 0 right now, the initial year where we have 1,000 people in our Wonderville town. So because of that, my reasonable domain is going to be including 0 to infinity here. The initial year would be 0, like I mentioned, and we cannot go to negative years. Now we're looking to define the y value to help us get the reasonable range. The y value is going to be going ahead and being what the equation equals to, which is the population in Wonderville. As a reminder, in Wonderville, we went ahead and started with a population of 1,000 people. So right away, I know that has to be an initial starting point. I cannot go below 1,000 people in this data set. What I know is that because the population's increasing, I will go ahead and have 1,000 to infinity being included as my reasonable range. The reason is because the initial value of the equation is 1,000 and the population is increasing, going up according to the given data. We can only go based off the equation we're given, nothing more, nothing less. Let's look at context example number 2. Reading it, the height of a bouncing ball measured in inches after x bounces are represented by the equation f of x equals 120 times the quantity of 0.75 raised to the power of x. Note that the height of the ball will decrease after every bounce. When we looked in our equation, the x was defined right after with the number of bounces here. We have to think about what's possible for a number of bounces. We cannot have negative number of bounces. And we can also start by holding the bouncing ball too. So that would be our 0 being included and going to infinity. Again, we can have 0 bounces. That's starting with us holding the ball and not bouncing it on the floor yet. And we cannot have negative bounces for the example, which is why I have 0 to infinity as a reasonable domain. We go ahead and talk about the range, which is the y value. This function is measuring precisely what it tells us in the beginning, which is the height of the bouncing ball. So because y is the height of the bouncing ball, let's think about what the height could be. The initial height is the 120, the initial value in our equation. Remember, that's the a like we learned last class. And that's going to be the highest it can be. Note that the height is going to be decreasing after that bounce. So that's why I'm going to be going below 120. Where I have to restrict my range is that I'm not going to have a negative height with this bouncy ball. I'm bouncing it on the floor, so I'm not going past the floor. I'm hitting the floor of 0 and nothing less. So that's why the reasonable range will be including 120 and going until the height of 0. The initial value of the equation is 120. That's the height in inches the ball is staying put at the start. After each bounce, we're decreasing the height, which means that I'll be so close to the ground, getting to 0, but never going negative in my height with the ground.